record on this computer.
Sir, will you be posting the slides after the class?
I'm sorry?
Will you be posting the slides after this class?
I'm sorry, Alex, I'm having a hard time hearing.
Will you be posting the slides?
Yeah. I'm sorry. I usually do that before the class, right? I will. Yeah, that I always do, Alex. Don't worry about it. You'll get the whole. You get the whole package. You'll get the slides. You'll get the PDF, and you'll get the video. We might have lost part of the because of this glitch. We might have lost part of it, but am I recording right now? Yeah, you will get it. Okay, so let's continue to where we left off. Okay, I think this is where we were. Am I correct? We're talking about the different, the PR value slideshow from current slide. Okay, so here we go. Okay, so we went through this. We talked about this. Like I said, keep in mind, okay, the width of the column. And like I said, the thing about the built-up columns is that when it's the B that governs, you lose quite a bit of the resistance because of the fact that it's fastened together. We went through that. A is a cross-sectional area. Like I said, this should be the cross-sectional area of the column, the size factor, okay? And then, of course, the B is the B of the column, not of the stud. The slenderness factor, we talked about this. We went there. Okay, now, same as the studs, okay, we have a limit on the slenderness ratio. In other words, the KL over B or the KL over D cannot exceed 50, okay? And that's the slenderness ratio, not the slenderness factor, okay? And of course, this is the KC over D, okay? And of course, you can appreciate that in a whatchamacallit, if in an exterior wall, you're most likely going to be, nailing your sheeting to the built-up column. So your B is going to be completely laterally supported, and therefore it's usually the D that will govern, okay? That's in a wall. And of course, you remember what this was. Okay, so this is the effective length factor, how it affects the buckling length of a column depending on how it's supported at the ends. And of course, in our case, we will always be using, okay, so now, like I said, this I find this a little bit, it's hard to imagine that you can get a fixed situation in wood. Very hard to do, okay? Very hard to do. I mean, you're going to have to put like a steel, and you have to encase your column inside that steel and all that. So that's very hard to do. This is also very hard to do, okay? The most typical is this. And of course, these are what you also have to be careful about. If ever you're building a balcony and your columns can sway out of its position, then the K value becomes really, okay? So this is something that you should keep in mind. But if you brace your system properly and they won't move, then you can always depend on K equal to 1.0, okay? So that's, and like I said, these are the ones that can really hurt you if your structure can move out of its, the column can move out of its original position, and then the K value becomes even greater than 1. And of course, that has kind of a drastic effect on how much resistance the column can have. So,
can I ask you when this is possible?
Well, for example, I build a platform in the back of my house here, and I build a balcony on top of the back of the house like this, right? And it's just standing like that. So is it possible that the wind can push this out of its place? Yes. You understand? That's when it's possible.
Like without having it supported into the.
Like in other words, if I don't brace this somehow, okay, the whole structure is relying on the columns to be able to brace this, the structure. So if I don't brace this, then it's possible the columns will be the ones that are going to try to resist the lateral movement. And if you can't create a fixed connection there and a fixed connection there, the whole thing's going to collapse on you. So it's possible, yes. Okay, so that's where you see, like, where can this move? Like, people build balconies and they forget to brace them, and then all of a sudden they wake up one day and it's on the floor. So that's where you see these situations occurring.
But so if it's laterally like supported onto the brick wall, uh,
Oh, as long as you got something, as long as you've got something to resist the lateral forces. In other words, like if you happen to have, okay, if for example, if I have a foundation wall here, right? If I have a foundation wall here, a big foundation wall, and I nail a nice piece of wood in there, right? Attached to my foundation wall, and it's well anchored. And then I put my studs here like this, okay? And then all of a sudden I put a good sheeting of plywood that will transfer any lateral load to here and then to the wall. Everything's braced. So then you don't have to worry about it. You follow? But
yeah,
if you don't have this transfer mechanism, in other words, from the like the wind that blows here or the load that if you don't have this transfer mechanism that can bring it to here and then the wall can actually resist that, everything's going to collapse on you. So that's what you have to be careful about. Okay. So yes, like as long as I have an element that can take the lateral forces and transfer those to the foundation, not a problem. You see? And a lot of people forget to do this. And then some people put a header there and then they put planks. And then the planks might not be able to be able to transfer. And then all of a sudden the thing gets distorted. So you got to, you know, there's things you can do to, to, so like if anything, we'll talk about this, you know, any time that you guys want. Like I said, if an element can take the lateral loads and you know that you can rely on it, by all means, just make sure that the loads can actually, the path that you're creating can actually bring the loads to that point, and then they can be resisted there. That's what you have to think all the time. What is the load path? In other words, how is the load going to transfer from this point to that point? I mean, and you know, like, I mean, like you have a beam, you have a load. Okay, so how is the load going? It's going to transfer there, then it's going to transfer there, and then it's going to transfer here, and then it's going to, and then, you understand? So that these are load paths. So you have to always think of how the load is going to go through your structure and what are the elements that are going to be able to eventually resist what you need to resist, understand? And here, of course, ultimately it's your foundations that are going to be able to resist so that the whole thing doesn't sink on you. And that's why you have to design these accordingly. Okay, so now, so LB and LD, unsupported length associated with total member depth or width. Okay, so therefore that's the LB or the LD. And the total width of the column, which is the thickness of the individual plies multiplied by the number of plies. So keep that in mind. If you're putting up a 2-ply, it's 2 times 38, 3-ply, 3 times 38, 4-ply, 4 times. So in other words, B is always the total number of plies. It's not just each ply. And D, of course, that is always the depth of the lumber. So it's either going to be 89 for a 2x4 or 140 for a 2x6. And now, bearing resistance, okay? To prevent, to prevent crushing, sill plates should be designed so that the factory resistance perpendicular to the grain QR is greater than the factory compressive force QF, okay? So what they're saying here, okay, the factor compressive resistance of the sill plate QF is equivalent to the axial force PF, which is what it actually is. So basically what they're saying here is, okay, so if I have 1-ply, 2-ply, if I decide to do a 3-ply, okay, if I decide to do a 3-ply column, okay, okay, and of course here I have my PF, okay, and of course I'll have a sill plate here that is sitting on. Well, just like we did for a stud, right? We went to find the QR value at the bottom of the stud wall table, right? And of course that is for one, that's the QR for one stud. So if I have a 3-ply, I'm allowed to take this QR value and multiply it by 3. And if that value is greater than my PF value, and I'm okay. Okay, so in other words, where do I go find the QR value? In the stud table. And the only difference is that that's per ply, and therefore if I have a 3-ply, multiply by 3. That's what they're saying here, okay? You don't calculate your QR, you just go find it in the table, in the stud table. I think it's, I don't remember what it is for, anyways, the values elude me right now. Now, One thing I want to talk about, guys, when it comes to columns, okay, is a live load reduction factor. Okay, now this is straight from the National Building Code. Okay, what the people have realized is that when you exceed a certain area, it's impossible that that area is going to be completely on that whole area. So you're allowed to reduce the live load by a certain amount. Okay, now this is a live load reduction factor. So when a structural member is supporting a tributary area of a floor greater than 20 square meters, so this is pretty good. In other words, it has to be over 400 square feet, which is, you know, like the 400 square feet is 20 by 20. Okay, so if you have a floor area that's more than 20 by 20, and this is only for live load, this does not apply to snow load. Keep that in mind. It's a live load reduction factor, not a snow load reduction factor. Snow load, there's no reduction, but this is only for occupancy loads. Keep that in mind. So when a structural member supports a tributary area of a floor greater than 20 square meters for use or occupancy, other than assembly areas. So in other words, you can't even use this in restaurants. This is just like in homes and offices and whatever. The specified live load may be multiplied by the live load reduction factor. Now, this is the formula, okay? The live load reduction factor is 0.3 plus the square root of 0.9 over B, and B represents the area or the tributary area of your column. Now, if you guys have a calculator, put 20 here for B and do the equation, and I think, if I'm not mistaken, you'll get this is equal to 1, okay? So if you put anything less than 20 for B, you'll get something bigger than 1, so that doesn't make sense. You don't increase your live load. So this formula only makes sense. In other words, this value has to be less than or equal to 1 for it to make sense. So if you put anything here smaller than 20, you'll see that the value of this will be greater than 1. Just try it on your calculator and see if what I'm saying is correct. So 9.8 divided by 20, take the square root, and I think that comes out to 0.7 plus 0.3, that gives you 1. So after 20 square meters, you can take advantage of slightly reducing your live load because of the live load reduction factor, because the areas are starting to get so big that the probability that they're all going to have so many KPAs, it diminishes with the bigger the area. So that's what this is, okay? And B is the tributary area in square meters. Remember, these are the units, square meters. So in other words, B is in square meters, okay? Now, design a built-up column for the following conditions. Okay, so specified dead load, 1 kPa. Specified live load, 2.4 kPa. Tributary area, 9 square meters. Okay, guys, look, just so that you guys can appreciate how simple it is, okay? Okay. Okay. I've got a column here. I've got a column there. I've got a column there. I got a column there. I got a column here. I got a column here. Okay, I got a column here. I got a column here, and so on. In other words, I got a series of columns, or I have a wall, whatever it is. Okay, guys, the concept of tributary width always applies. So what you do is you take halfway between here and here, and you're going to say and then you're going to say that this load is going to go this side, this load is going to go that side, and then you do the same thing here, halfway between there and there. So you're going to say this load is going to go on this side, and that load is going to go on that side. Then you take halfway between those columns, this column and that column, and you say that load is going to go here, and that load is going to go there. And then you take halfway again between here and here. And then all of a sudden, guess what this is? This becomes your tributary area for that column. And you do that for all the columns. In other words, always take where it is halfway to the next supporting element. It could be another column, it could be a wall, whatever you care. Halfway between that and the next supporting element, halfway. As long as you go halfway, 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 you will be able to determine so for example, if there was no columns on this side, you can appreciate that this would be the tributary area for this column. You see? Okay, and if there's nothing here, this will become the tributary of that column. So, okay, so that's how easy it is to calculate tributary areas. You simply worry about where is the thing sitting and what's the supporting element adjacent to it. It could be a wall, it can be another column, it can be whatever you want. Okay, it can even be a beam, I don't care. As long as I know that the loads are going to get transferred between there and there, then between there and there, I can actually calculate the tributary area. So that's how, So when it comes to simply supported members, okay, like we have in steel, okay, and when we have in wood, then this is the fastest way of calculating the tributary area. So now, the unsupported length of the column is 3 meters, which is reasonable, about 10 feet, okay? And we have dry service condition. Guess what I'm gonna do? I'm gonna give you one where we can go straight to the tables, right? Untreated wood, very nice. Column effectively pinned at both ends and concentrically loaded. Wow, so yes, 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 okay? Use SPF stud grade lumber, which what you should be using, okay? So basically all you gotta do now is you gotta get your design loads. So therefore you take case 1, always 1.4 times your dead load. And then case 2, combination 2 I should say, 1.25 times your live load. And of course the higher of the two, so therefore this one is the one that governs. Now, how do I calculate PF? PF is very simple, okay? PF is equal to the factor load times my tributary area. And if you look square meters, I end up in kilonewtons. Those are the right units. That's going to be the axial force coming down right through the column. And this is going to give me an axial force of 43.65. Let me write this down. 43.65 kilonewtons. So now I've got my PF. I need to find a PR greater than my PF value. When I go to the table, the only thing I have to worry about is that what is going to be the length of my column. I know here we're talking about 3 meters. And of course, the species and the grade is something else I have to decide before I go to the table. Of course, PR has to be greater than PF. And therefore, as soon as I find a PR value in the table that's greater than the PF value, I'm okay. So here, I go to the built-up columns. Now, oops. Like this is the low duration standard. Yes, 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 yes. So that means I said yes to all these questions. And of course, therefore, I go with an SPF number 3 with a length of 3 meters. I go to the built-up columns. And of course, now I start with a 2x4. Now let's see what's going to happen with a 2x4. So I have a length. So this is where I am. This is my grade. Okay, so this is my grade. And like I said, these are my species right here. Okay, so I'm going to be looking for something in here. So what I'm looking for is, can I get away with a 2x4? 2-ply, 3-ply, 4. So therefore, there's nothing greater than 43. So therefore, I can't get away with excuse me, I can't get away with a 2x4. So therefore, I have no choice than to see if I can get away with a 2x6. So now I come here and I do the same thing. Like I said, here's the grade of lumber. Here's a species right between these two lines. Okay. And of course, this is what's the most critical thing about a column is its unbraced length. And therefore, look at this. Okay, so I go up. So I know that if I use a 4-ply, okay, so I use SPF 38 by 140 4-ply, just like we would specify for a built-up beam, okay? Okay, L equal to 3.0. We have PR equal to 75.2, greater than my PF of 43.6. And there's my answer right there. So I have a 4-ply 38 by 140 SPS stud grade nailed together as shown in figure 3.2. And of course, it has to be nailed, in other words, for it to have that resistance. And I have a PR value of 75.2. And I don't care if it's almost twice as big. It shouldn't be less. So because I'm kind of, I have no choice but to keep on adding a ply. And I can't have 3.5 plies. I either have 3 or a 4-ply. And in this case, I ended up with a 4-ply. And guys, when it comes to columns, I really don't care if I have more resistance than I actually need, because there's columns are very critical. If they fail, everything else comes down. So it doesn't hurt to have them over designed. Is this clear to everybody? Is there any questions so far?
So far, so good. Thank you, sir.
Good?
Yeah.
Okay. Now, now, of course, I'm going to do a built-up column for the following conditions. Of course, okay. Specify dead load 0.8 kPa. Specify that 1.9 kPa. Tributary area is 25 square meters. Oh, I'm getting to be pretty big area. The unsupported length is 2.2 meters, okay? I have dry service conditions. I have untreated lumber and column effectively pinned at both ends. Great, so I can still use the tables. The only thing is that because this exceeds 20 square meters, I'll take advantage of the live load reduction factor to see if I can reduce my PF value, okay? So basically, use SPF number 3 solid lumber, of course. Okay, so now for the factor loads, okay, case number 1, 1.4 times my dead load. There is my, for load combination 1. Now for load combination 2, what I'm going to do is I'm going to calculate, since B exceeds 20 square meters, since B exceeds 20 square meters, then I can take advantage of the live load reduction factor, okay? And therefore, I simply put in the equation, and then I'm getting 0. So I can take my live load and multiply it by this factor and reduce it by, of course, it's about, you know, a little bit, reduce by about 8%. So now, the formula becomes 1.25D. That doesn't change for load combination 2. But here, instead of just multiplying by 1.5, I will also multiply by my live load reduction factor, but only the live load, never the dead load. It's a live load reduction factor. So I put my values in, and I come down to 3.64 kPa. Now, if I wouldn't have put this in, of course, it would be slightly higher, okay? So that's how the live load reduction factor works. It only applies to the live load, okay? And then you multiply, but these live load factors don't change. It's just a live load reduction factor that you incorporated here in this load combination. Now, of course, the same thing, factor load times tributary area, that gives you your PF value. I have a PF value of 91 kilonewtons. So 91 kilonewtons, and I had an L of 2.2, I believe. Does everybody remember what the L was for this problem? We have an unsupported length of 2.2 meters. 2.2 meters, and we have a PF equal to 91. Okay, so basically what we want to do now, because we say yes, 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 okay, we can go to the, okay, so the checklist for built-up columns, like I like to do this, especially when it comes to column, guys, okay? So is the load duration standard? Yes. Is the service condition dry? Yes. Is the material free of incisions and or fire? Yes. Is the column effectively pinned? Yes. Okay. Is the load constraintly loaded? Yes. So therefore, I said yes to everything, and therefore, I can go ahead and go to the built-up columns. And of course, again, let's see what happens here. So I have a column that's 2.2 meters long. Well, first of all, here's my grade, and here's my length, and here's my species here again, okay? So is there anything that will exceed 91? So here, nothing works. So therefore, I can't use anything with 2x4 lumber. So since I can't use 2x4 lumber, because 2x4 lumber, guys, is a little bit cheaper to buy than 2x6s. That's why I like to, you know, see if I can use 2x4s. And of course, now I come back to here. Same thing, back to my species, back to my length. And of course, only look at this with the values that are here. And I can come across here. And I end up here, 94.7. Okay, so there we go. So 94.7 is greater than 91. Therefore, I know I can use SPF, okay, 4-ply, 38 by 140 lumber. Nailed, of course, according to the schedule. Okay. Okay, and there's my answer. Okay, and I'm pretty sure if I wouldn't have used a live load reduction factor, I probably couldn't find a value of PR. And I'm sure of it, because it would probably been higher than 91. Okay, so that's, you're allowed to do that. And, you know, so as long as your area exceeds 400 square meters, I mean, it's approximately 400 square feet, 20 square meters. I shouldn't even talk in square feet, because that's me, old school. Okay, so here we go. So we have used 4-ply 38 by 140 SPF stud grade nailed together as shown in figure 3.2. And of course I have 94.7 and greater than the PF of 91. And of course, guys, do the assignments. It does get you ready for the exam, okay? Now, the reason why I don't do one with wet conditions here is because the only place that we're going to be using built-up columns are going to be to support lintels, okay? And inside buildings, so therefore, but if you guys want, we can go through a whole example where we can throw everything into the mix, but then we'll have to do everything from the equations, just like we did with the studs.
So for built up columns, it's always going to be dry.
No, no.
Just in our like.
You mean what? In real life, no. All I'm saying is that 99% of the time, your built-up columns are going to be in a standard, dry, non-treated situation. Okay.
Okay.
But don't take that attitude that it's always going to be that. No, it can be in a moist environment. It all depends where you're designing. And if it is, then you have to, the same way that we calculated the studs for when we answered no to the question, you have to do the same thing with the formulas for the built-up columns. They're exactly the same formulas. I don't know if you guys can see that, but they're exactly the same formulas, and we go through exactly the same steps. So, and trust me, we are going to be, when we get into formwork, we're going to be applying that a lot, because formwork, we're going to have bearing walls to support our formwork. There's going to be no sheeting, so everything's going to be done, all the calculations are going to be done using the formulas. So you're going to get lots of practices on how to use the formulas when we do the very last lecture on formwork. So don't worry about it, okay? So I know like where the thing will come up again, and I know where you guys are going to be able to practice some more on a given situation, okay? So are we all good?
Yes, sir.
Okay, so what we'll do right now, what time is it? Do we have time for your lab today? Oh yeah, we have lots of time. My God, here I am. So hey, so let's, okay, so there we go. Close this, minimize this. We're still recording, aren't we? I hope.
Yeah, we are.
We are, okay. I just want to make sure. You guys see the lab right now?
Yeah, we see you.
Okay, I just want to make sure because, you know, here it's very clear for me because I would definitely see it on my, okay. I would definitely see it on my, okay, so guys, like I said, you're not going to get this lab. So whatever I show you here, make sure you write it down, okay? So take your time, take out paper. I'm going to expect to see these in your calculations. You're not going to be getting this, but I will be walking you through the whole thing, okay? So let's start with what we want to continue with our project, okay? So basically, this was, we're going to be at the very last element that we need to design in wood, okay, in the basement. So basically, if you remember, this was the overall size of our foundation wall. We had decided to put a beam going down the middle, and we decided to put 4 columns. And of course, now this becomes a tributary area of each column. And because the tributary areas are all the same, each column is going to be exactly the same size, okay? And next week, when I ask you what size columns that you ended up getting, I want an answer. And then after that, I'll show you how to calculate to see if you have enough bearing resistance between the column and the beam. And I'll do that next week, okay? So remind me to show you how to check the bearing between the column and the beam, okay? So, okay, so all you gotta do now, of course, you're gonna have to draw the sketch here, okay? And of course, you have to show me what the tributary area is for each column, and tell me what the tributary area is. You know, take a snapshot of this, take a screenshot, I don't care how you do it, but this is what you're gonna have to show me in your calculation sheet. So you always start with the geometry. Once I've established my geometry, then I worry about my loads, and of course the loads don't change. 1.0 kPa was our dead load, 1.9, okay? And now, people have asked me, what is the unbraced length of the column? Well, it's going to be the height. We're building a modest home, okay? So we'll assume that we're going to have 8-foot ceilings in the basement, okay? We're going to assume that, and therefore we'll assume that the column is 2.44 meters, okay? It can be shorter because if it's sitting underneath the beam, and if it's 8 feet to the, it all depends, but just assume it to be 2.44, okay, to be the length of your column. And therefore, when you go to the table, if you have values for 2.4, okay, take values of 2.4, that will be close enough. But this is the unbraced length of your column, okay? So there you have it. Okay, so that's just to guide you on what you have to do for, to move your project along. Is there any questions here? I think it's pretty clear the way I've shown it here. I don't, is
Yeah,
anybody?
it's good, sir.
It's good, right? Okay. Now, may I go on, or does somebody still copying something? Just let me know. I don't want to just rush through this. Okay, so now, I like to show you, okay, now that we've got the geometry, now that we have our loads and everything else, okay, I'd like to show you how you would size the footings underneath these columns, okay? I'm going to show you how you would size the strip footing underneath this wall, okay? And of course, once you've designed the size of the column, if you wanted to, you can then decide to actually, from what we learned last year in reinforced concrete, you can actually design the thickness, okay? And to make sure that if like you can actually use what you learned in concrete to design the thickness, okay? But all I'm going to do is give you the size of these, okay? Now, so for the isolated footings, we know that P, okay, the load, because here we're going to be talking about allowable bearing pressure. Therefore, we do not factor our loads when we size columns. I don't know if you guys remember that from concrete last year. So therefore, I would add my dead load to my live load. I always use a specified load, and I multiply that by my tributary area. Therefore, I had 1 kPa as my dead load, 1.9. Guys, this you have to write down in your notes. So either write it or take a snapshot at the end of the slide, whatever you want to do, or or go back to the video. But you're not going to get this you're not going to get this PowerPoint, okay? So here, 1.0, 1.9, and of course, this is my tributary area, and therefore I end up getting, so the axial force, that is coming down to the column, the specified axial force is 39.9 kilonewtons, okay? So what I need to determine, right? So basically, here in cross section or in elevation, here's my footing. I have a column coming down here, okay? And it has a load coming down of 39.3 kilonewtons. And therefore, I have an allowable soil pressure here. And based on that allowable soil pressure, okay, I should determine how big this footing has to be so that I don't exceed Q allowable. That's all it is, just like we did, in concrete. So basically, now here I'm going to assume a soil pressure, 50 kPa, guys. Can I strongly recommend, okay? Can I strongly recommend that, remember this for the rest of your lives, okay? If you're ever going to get into this, okay? One of the bad practices, and guys, one of the bad practices that most of us do is that on our drawings, okay, we always write, okay, footing size, okay, based on assumed soil pressure of 50 kPa, okay. Contractor okay, to verify if in-situ soil has at least a bearing capacity of 50 kPa. And that's what we used to put on our drawings. And we figured we covered ourselves because we put the onus on the contractor to make sure that whatever soil condition he encounters at the job site, he has to confirm that our assumption of 50 kPa is good. And that's what everybody was doing until finally one person went to trial and the judge condemned the engineer for doing this. And because of that, this is no longer a good thing to do. Now there's case law out there that tells you that if you are going to assume 50 kPa, you should insist that the owner pays for a soil report and have the soils, the soils lab confirm that the bearing capacity that you've assumed is what they're going to be actually encountered on the job site. So don't ever put this on your drawing anymore. That is definitely bad. Okay, I know the poor engineer that got condemned. He's a guy I know. Okay, I know his name. And I also know the judge that rendered this judgment against him. So I know them both. And I can tell you that this is a very bad practice. So whatever you assume here, if you're going to be actually doing this in real life, you're going to have to make sure that you twist your client's arm, spend the money, get the soil tested. Okay, as a matter of fact, have the soil tested even before you do your drawing. So this way you already have the information and you can do it without any assumptions. Okay, and then you'll be able to do everything correctly. A lot of people don't like to spend the money, and unfortunately you end up getting with the problems. So like I said, this is assumed. And if I was doing this in real life, I would actually mandate a lab to go out there and give me the QA. That's what I would actually do. Okay. Now, of course, the area of the footing is my force divided by my allowable soil pressure. And in this case, it's 0.79 square meters. And of course, how do we get a nice square formula? Footing, we simply take the square root of that. It's about 0.9 by 0.9. Therefore, it's safe to assume that our footing size are going to be 3 feet by 3 feet. So if you're doing your drawings in Imperial, that's the size of footing you're going to be putting on that drawing S1 for the wood project. That's 3 foot by 3 foot footing. Okay, an isolated footing. Okay, like I said, I don't know the thickness. I haven't designed the footing yet. Okay, but if I wanted to, I can see if I can design this footing without any reinforcement. Okay, but the standard thicknesses that we have in residential, because the loads are so light, we usually put about 10 inches. Okay, that's the usual thickness for residential. But I would actually check to make sure that I can do this without having any reinforcement, or I would actually design it as a reinforced footing just like I did, okay, and confirm that 10 inches and then specify the reinforcement on my drawing. So I would either design it as a plain, in other words, unreinforced footing, or as a reinforced footing, either way, but it would have to be designed. All I'm doing now
So
is
you're leaving the choice to us either to design it for as a reinforced or not. Or
I mean, like you can do both. We learned how to do both, right? We learned how to do both, Nermin, and it's up to you to decide. Like I showed you in certain cases that a plain footing is as advantageous as one of the assignments I showed you. I took such a light load that the plain footing ended up being about the same size as a reinforced one. Understand? So it's up to you, but that's something that you do in concrete. So if you guys can dig up your concrete notes, and if you had to do this in real life, you should, that would be an additional calculation you'd have to do for this project. Understand? So now, so that's the size of the isolated footing. Okay. Now for the strip footing. Okay. Now the strip footing, of course, you have to be able to discern all the loads that start from the roof and come all the way down on the exterior wall, and then all the way down to where the strip footing is going to be underneath the foundation wall. Okay. So what you have to do then, okay, is you have to look at the roof. Okay. How's the roof made? Okay. Does anybody know how we're going to construct this roof? Does anybody have any inkling how you build a roof on a residential house?
Trusses.
Okay, so we're going to, okay, great. So here we're starting. We have trusses. Good. We're going to have trusses. Okay. What else are we going to have?
Asphalt shingles and sheathing.
Good. Asphalt shingle and sheeting. Great. There, we're getting there. What else are we going to have?
Insulation, ventilation.
Insulation. Great. I love that. What else are we going to have?
Drywall.
Sorry?
Drywall.
Exactly. We're going to have a drywall on the ceiling. Fantastic. There. Now you guys are starting to see sense. So this is the typical construction materials that we're going to have to build a roof structure. Okay. So now that we have an idea of what materials, okay. So basically we have asphalt shingles. Okay. Now guys, I've calculated this for you, so you don't even have to worry about it. Okay. They weigh about, this is the weight of the asphalt. These are the cheap ones. Okay. Do you guys know anything about asphalt shingles?
Yeah, we just learned about them in spec.
Okay.
In
Inspection.
inspection. Yeah.
Yeah,
Okay,
inspection.
and what? Tell me what you learned, so this way I won't repeat anything. What did you learn? Do you know how you determine the weight?
No, we didn't learn
more
that. We
the
just
aesthetic.
learned what to like check for.
In other words, you check for
damage.
curling, you check for that's cracking. That's what you
Yeah.
check
exactly.
for, right? Okay, and can't you simply ask the owner when was the last time he replaced his roof?
Yeah.
That's about 10 or 15 years or something, no?
No, I'm just saying, like, the best thing to do is to tell the owner when was the last time you replaced your roof. You understand?
Maybe they don't know.
Well, if they don't know, then tell the owner that. Pardon? Anyways.
They can always just lie. No one's going to fall back on you. So
No, if they lie, it falls back on them. You know that, and you put in in la page de déclaration, le propriétaire a déclaré que le toit était fait il y a 5 ans. You understand? And you write that in the declaration paper. So how does it fall back on you? Anyways, I don't want to get into it. Okay, so you guys learned how to inspect a roof. Great. So I won't get in. What I'm saying is that there's a roofing unit that you guys might not be aware of. It's called a square. Okay. In roofing, a square measures 10 feet by 10 feet. That's a square. Okay. 10 feet by 10 feet. Okay. So in other words, 100 feet squared for a roofer is a square. And they use this. Okay. For example, they'll say, oh, your roof is about 20 squares. That means it's 2,000 square feet. Okay. Now, when you look at shingles, okay, when you look at shingles, and if they say 210, okay, that means that the shingles, when they're laid out, they're going to weigh 210 pounds per square, per 100 square feet. So therefore, each shingle is going to weigh about 1.2 pounds per square foot, okay? So you can have shingles that are 210, you can have shingles that are 225, you have shingles that are 235, and just to give you an idea, this will last you 15 years, this will last you 25 years, and this one will last you 35 years. So the heavier, the more, you know, the more tar there is, the longer the roof is going to last. And this is how you determine the weight of your shingle, okay? So here, when I said that the shingle weighed 1.1 kPa, I took the cheapest one. I took a 210, and I converted the PSF into kPas, okay? So that's just for your general information. So if ever you hear a square, just remember, a square is 10 feet by 10 feet, that's 100 square feet. And if ever you talk to roofers and they talk about squares, that's what they're talking about. Now, that's something you should have learned in your estimating class, you know, because some people do estimate by squares. Okay, tar paper, 15 pounds. See, 15 pounds means that it weighs 15 pounds per 100 square feet. That's the tar paper. If you see a 45-pound tar paper, that's 45 pounds per 100 square feet. So 15 pounds per 100 square feet, this is what it turns out to be in kPa. if you guys are interested, 1 PSF is equal to 47.88 pascals. Okay, remember it's pascals, not kPa. So therefore, that's how you convert your PSF into pascals. Okay, so you have a 15-pound tar paper underneath your shingles. Then you have your 1/2-inch plywood. That's what it should weigh about. And then after that, you have the roof truss. Now, I'm assuming that they weigh about 2 pounds per square foot. We can verify this once we actually design our truss, but I think that 2 pounds per square foot is reasonable. Just like when I assumed the weight of the joist for the steel, at 2 pounds per square foot is reasonable. So that's assumed, and ultimately I can come back and check it if I have to. Of course, I have some insulation. Okay, in this case, I put 16 inches of insulation in the ceiling because I want to keep my heat in the house. That ends up being 0.2 kPa. And of course, standard home, always half-inch gypsum. The only place that you use 5/8 in a home is in the garage, okay, for the fire rating. Otherwise, all the home is made with half-inch gypsum. And that's going to be the dead load of the roof. So therefore, it's about 5.9 kPa. I'm going to say 0.6 kPa. And that's reasonable. In other words, about 12 pounds per square foot for a roof structure. That's pretty good, okay? That's for residential, that's pretty good, okay? So any questions here? Easy enough?
So just for general information, when you were talking about the asphalt shingles and how they come in like 235, 24, like where's that specified? Is that like specified like when you buy?
They used to specify it right on the package.
Okay, so it's like, oh, it would be on the package, we could find it.
Exactly. In other words, if they say it's a 15-year shingle, most likely it's a 210. They say it's a 25-year shingle, most likely it's a 225. They say it's a 35-year shingle, it could be a 235. You understand?
Okay.
So that can be right on the package. You understand?
And that's 235 pounds per square, or?
Yeah, 235 pounds per 100 square feet. So it comes out to
Okay.
be 2.35 pounds per square foot. You understand? And that's why don't confuse it like it's per square. It's always per 100 square feet. In other words, whatever you have there divided by 100, just like I did here. This is 15 pound. When they call it a 15-pound tar paper, that means that this thing is going to weigh 15 pounds over 100 square feet. You also have 45-pound tar paper. You understand? The better ones. Okay, and that would be 45 pounds per 100 square feet, and therefore it will be slightly heavier. Okay.
Thank you.
Okay, guys. Like I said, okay, is everybody good with the roof now?
Could you give me a second?
Sorry?
I'm just writing down this information.
Yeah, sure. I mean, take your time. I mean, I'm good here till, I think my wife says supper is going to be around 7 o'clock. So you guys are good to stay till 7? Not a problem. I'm just kidding.
What's for supper?
Okay, I'm done.
Spare ribs.
Nice.
I'm jealous.
Well, and I don't want to get into it. I'm looking forward to it. So they take 2.5 hours to cook. So that's why it's going to be a slightly late supper. So I'm not worried about it. Okay. Sounds good, guys. So far, so good. Okay. Now, after that, what other load are we going to have on the roof?
Maybe the gutters. I don't know.
Snow.
Snow. Okay. Snow. Good. So the other thing that we're going to have on the roof is a snow load. Okay. And we've calculated the snow load in our steel, right? To be 2.5 kPa. If I'm not mistaken.
I have a question. It's kind of off topic, but do we have to account for the ridge vents and like the gutters?
When you consider what that thing would weigh, about
It's minimal.
like you're talking about like the soffit. Okay. Let me just put it to you this way, Alex. Let me just show you, like, can I just say, so Alex, you're the one that asking me, right? Sorry, I just want to make sure.
Yes, it was me.
I hear the voice, but I don't see, like, I see the name now, but okay. Here is my roof structure, right? Okay. So far, I said that my dead load of all this was about 0.6 kPa, right? When I'm going to be calculating the actual width of this roof, I'm going to go from there to there. You'll see this later, okay? Your gutter is sitting here. You understand? I don't know if you guys ever picked up a gutter. I can pick it up with one finger, even if it's 10 feet long. So it weighs nothing, right? The fact that I don't have any gypsum here, and I'm going to assume that I also have gypsum there, it's going to compensate for the weight of the gutter. Does everybody understand what I'm saying? Okay.
Got it.
And don't forget, guys, for footings, we have a factor of safety of 3 for QA, right? If I overlook this gutter, what do you think is going to happen to my QA?
Nothing really.
Exactly. So guys, worry about calculating your snow loads correctly. Worry to estimating your dead loads approximately. Don't worry about these little details because, you know, like for example, let me go back. Let me go back, okay? Like out of all of this, okay, like for example, this is important. This is important, you understand? If I don't add this, you think it's gonna make a big difference at the end of the day? You understand? This is important. You understand? Like these are values, like this is important because it's there, okay? And if this is slightly overestimated, it's gonna compensate for the, like, you know, if we really wanna get picky, I hope you guys, I mean, if you really wanna get picky, I hope you guys realize, I mean, here is my roof truss, okay? Here's my roof truss, okay? And here's my bottom cord, okay? Before I put my gypsum, I have to put furring strips on the underside of my bottom cord, and then I put my gypsum. What does this add to the weight of the structure?
Yeah, that's probably more than the just the.
It's peanuts, guys. Like it just measures 1.5 inches by 3/4 of an inch. You understand? It's like it's very like it's, you know, there's going to be a couple of lights in my ceiling. Am I worried? You know what I mean? So you follow what I'm saying? Like guys, like just, you know, I want you guys to be practical. I don't want you guys to worry about become academics. You understand? Like if these things are really a concern, we'll go find the weight of it and see how much it weighs, and then, you know, add it in. I mean, or you can say, you know, 0.2 kPa for furring strips and gutters, and make an allowance. You follow what I'm saying? Do something if that's really, you know, all I'm saying is that these are things that I've never worried about because they're very, like the 15-pound tar paper, I shouldn't even have put it in, but I just want you to understand that that's a good roof usually has a 15-pound paper underneath the asphalt shingle. Some people put the asphalt shingles directly on the plywood, and other people like to put the 15, what the 15-pound tar paper does, it acts as a backup that if ever you have a defect in one of the shingles, instead of the water coming into the house, the tar paper might prevent it from leaking. You understand? It's a cheap backup. If I were to do my roof properly, I would probably use a membrane all the way up and then put my shingles over it. That would even be safer. You understand? So now let's go on. So here we go. Now this, like I said, we calculated a snow load for the steel project. We ended up getting 2.5 kPa. You want me to write out the equation here? I can prove to you that it's 2.5 kPa if you guys, okay? But this was a snow load. Since it's Montreal, the snow load on a residential house is the same as an industrial building, so therefore it's 2.5 kPa, okay? The only thing about the residential is that, anyway, I don't want to get into it, is that you don't have to worry about the other shape factors. When you can just take everything to be a uniform load. Now, the exterior wall, okay? We know that we're building the exterior wall. That's going to be, you know, so we have our exterior wall here. We know we're going to have some kind of a stud, and we're actually going to be designing the size of the stud, okay? Now, we won't even be designing, well, we will be designing it, but the stud size is already determined by what? The stud size is determined by the amount of insulation that we want to put in our wall. So even if we can get away structurally with a 2x4, because we want to calculate the cavity here and put more insulation, we always make the studs 2x6s. So that's becomes standard. The only difference is that since we're using 2x6, can we space them at 24 instead of 16 or 12 inches? So that's where we might be able to save on some studs. So as far as the width of the stud here, this is going to be a 2x6, okay? And of course, we're going to have some insulation. So that's going to be, okay, so that's going to be like what, and of course, we're going to have 2 sill plates up here because it's a bearing wall. We're going to have our stud here. We're going to have our stud here. We have our insulation. I should change color so you guys can, I should have put, yeah, Pink Panther. So I have my insulation in here. And then on the outside, excuse me, yeah, just change color again. on the outside, we have our sheeting, our 1/2-inch sheeting. And then of course, on top of that, we're gonna have, it's a very inexpensive home, okay? So, I mean, I'm not even gonna, I don't think I even calculated this, but you're gonna have your sheeting and then you're gonna have some furring strips, okay? Oops, sorry. Some furring strips. And then on top of the furring strips, of course, you're gonna have your aluminum siding or your siding. It can be aluminum, it can be vinyl, you're gonna have your aluminum siding. Then on the inside, you're gonna have your 1/2-inch gypsum board. So that's basically your wall construction. So therefore, we're gonna, now, aluminum siding, that doesn't weigh very much, 0.3 kPa. 1/2-inch plywood, the same as on the roof, whether it's on the wall or on the roof, it always weighs the same thing. And then after that, we have our 2x4 studs at 24 inches. We'll confirm this with our design, but this is, I think it's safe to assume that they're gonna be spaced at every 24 inches. For a 1-story building, that's usually the case, but we will confirm it with our design calculations. And the 150 inches of bad insulation that we're going to be putting on the wall, okay, that weighs 0.8 kPa. And of course, a 1/2-inch gypsum. So that's what our wall is going to weigh. Now we got a dead load of our wall, okay? And that should add up to 0.35 kPa. And you notice I always like to round up to 0.4 kPa. Now we got the weight of the wall. What's the next thing that's coming down? We have our roof, we have our wall. What's the next thing?
First floor.
The floor, okay? So we have our floor. What's the dead load of the floor? We've already calculated it. Do we need to recalculate it?
No.
No, we already know that it's 1 kPa. We've been using 1 kPa to design our joists. We're using 1 kPa to design our beams. We're using 1 kPa to design our columns. Does that change anything? So it's 1 kPa. What's the live load for our floor?
1.9.
One what?
1.9.
1.9.
1.9.
1.9. In other words, residential has to be designed for 40 pounds per square foot, which is 1.9 kPa, okay? So that's the minimum live load you can put on a residential floor, 1.9 kPa. Remember, this is the minimum. Now, after that, what do we have?
What do you mean? What do we have? Like the
And the loads are going down to the footings. What do we have after the ground floor?
The basement wall?
Yeah, the foundation wall, right? So then we have the foundation wall. Now, like I said,
Can you go back? I just forgot to. I just missed writing the last thing.
here, these two. Yeah, you can always go back to the video and look at the video. But there you have it, okay? 1.0, okay, sounds good. Now, after that, of course, we have our foundation wall, okay? And like I said, in residential, yes. Somebody have a question? Omar, yes, go ahead.
No, I don't. I'm sorry. Sorry.
No, it's okay. I like, guys, it's a lab. We're here to be practical. We're learning how to do things. And if you have general questions, ask me, because this is a good time for us to have these discussions, you understand? So first of all, how are we doing time-wise? I never had the time. 4:36.
Yeah, 1 hour.
We have a whole hour. Wow. We'll have time to talk about who's got the best joke for the day. Okay, so basically, guys, when it comes to residential construction, and I'm telling you this, okay, residential construction, foundation walls, okay, the most typical width of a foundation wall, okay,
8 inches.
8 inches if it's siding, okay. If the outside cladding is siding, it's 8 inches. If you have masonry, okay, if you have masonry, it should be 10 inches, okay. Why are they thicker?
So they can hold the.
So that you can create a seat for the masonry. Okay, so if it's masonry, it's 10. And when it's no masonry, it's 8 minimum. Okay, so that's how you keep in mind.
So
if you want to make them 12, make them 12. It's up to you. Okay, but 8 and 10 is the, let's call it, typical sizes for residential foundation walls. Now we have in our case, we have very, very we have siding, so therefore now 8 inches is I know it's 0.204 meters, but don't get technical on me. We're going to make the wall 8 feet high, right? You understand? And this is the unit weight of concrete, right? 23.6. You should have this like the back of your hand. You did this so much last year that you should know the unit weight of concrete is 23.6 kilonewtons per cubic meter. So now I'm going to get a uniformly distributed load. In other words, the load that's acting along the footing for the wall. Now, the next thing I have to assume is the footing itself. In other words, the footing is going to add a weight. And then once I check the size, I can also come back and see if my assumption is correct. So I'm going to put something reasonable. So for the footing dead load, this is assumed, okay? So I'm going to assume that it measures 30 inches by 10 inches, and therefore, because these are the typical sizes that we use for residential houses. And if they happen to be 36, well, I'll come back and check again. So the unit weight of concrete times the height times the width. Okay, so here I'm using one. I'm even assuming a 1 foot thickness, not even 10 inches. I'm going to assume 1 foot thickness, and I'm going to assume a 30 inch or 30 inch width. So therefore, this is an assumed weight of the footing. So now I've got all my loads coming from the roof all the way down to the soil, because that's what you have to calculate in order to calculate the size of the footing. In other words, you have to calculate all the loads coming down. Okay. And don't forget, when we calculated the isolated footing, we forgot to add the weight of the footing itself, and that's something I should go back and check to make sure that that 3 foot by 3 foot is sufficient. So this is what you have to look at, okay? Now you look at your building in cross section, okay? And this is what your building looks like in cross section, okay? And as a matter of fact, this is going to be similar to your drawing number 3. Remember your drawing number 3, it all depends. This is a top loaded beam as opposed to a side loaded beam, okay? But basically, here's my truss, here's my wall, okay? So here is what you have to remember, okay? All the loads all the snow loads up here, okay? I know that this is gonna go here and this is gonna go there, okay? So, and then all the load of my roof structure here is going to go there, and all the load on this side is going to go there. Okay, so therefore, that's the load path of how the loads are going to go down. Then the loads here are going to go down the wall. All the loads on the floor here are going to go through here, and then all the loads, and eventually, they have to be resisted by the soil here. So I'm going to start adding the loads here, the load here, the load here, the load here, the load here, until I've added all the loads coming down. And then what I need to do is, of course, look at the tributary widths that contribute to a uniformly distributed load acting along the whole, you understand, length of the wall. So that's what I'm going to be doing. Does everybody understand what I'm doing?
Yes.
Yes.
Okay, so this is why, like geometry is key to everything. Without geometry, you can't do anything. So this is where, okay, so I showed you this, and now, of course, so now this is what I actually see. I only worry about half because the other half is going to be taken care of by the other wall and the other footing. Okay, so therefore, this becomes a tributary width for my roof structure. This becomes a tributary height for my wall. This becomes a tributary width for my floor because I have a beam there. This becomes the height of my, like here, I've already calculated this, and then here's the assumed size of my footing. So I start, okay, at the roof, I have my dead load plus my snow load times my tributary width. So I have 0.6 plus 2.5, and everything's done as specified loads. Remember, guys, because we're using Q allowable. And what's my tributary width? Well, from my drawing, I see that my tributary width is 4.69 meters here, okay? Now, of course, I was being a little too religious here. I should have used 4.7, but in other words, so what's happening right now is that from the roof, I'm having a distributed load that's going all along the wall, okay? Sorry, this thing's in my way, okay? And this distributed load that's going all along the wall is 14.54 kilonewtons per meter. So for every meter wall, this is the load that's acting on it. So that's just from the roof. Now, The wall, very simple. I have the weight of the wall in terms of a pressure of a surface area. If I multiply that by the height of the wall, I'm going to get the distributed load that's acting along here. So, sorry. So the wall, I have the dead load of the wall times the height will give me the distributed load that's acting along the wall. Okay. And of course, 0.4 kPa is what we calculated the weight of the wall. We multiply that by the height of 2.44 meters, an 8-foot wall. Okay. And that gives me 0.98 kilonewtons per meter. Now, here you got to be careful. I mean, if you make the mistake, yes.
How's the height has a unit of kilopascal?
Well, it's simple. Very simple. Here's my wall, right?
Yeah.
Here's my wall. I calculated that the plywood on my wall weighed 0.7 kPa.
No, I think it's mistake. 2.44 meters, not kilopascal.
Oh, this is a mistake. This should be meters. Sorry, that's a typo. Okay.
Oh, okay.
So I'm sorry. I apologize. So thank you, Rania. Thank you for correcting me. I should correct that. Okay, that's a typo. Okay, so this should be 2.4 here. This is this. So that's a typo. You want me to correct it right now? For some reason, I can't escape from.
It's okay, sir. We get it.
Yeah, but I want to correct it because
okay.
I might never use these slides again, guys, because I just realized I'm going to be retiring soon. So I'm going to correct it anyway. So
what?
Well, I mean, I'm turning 65 this month. So
happy birthday, sir.
When is your birthday?
Sorry?
When is your birthday?
It's in March.
But say.
It's in March.
Give us a week, sir.
It's in March. It's sometime
in March break or after?
It's in March. How's that?
Yeah, March break.
Sure, mine's too is in March. When's yours?
March 9th.
March break is from the 15th to the 19th. Okay, so guys, like I said, I wanted to fix that. You're right. This is meters. See what happens when you work at 4 o'clock in the morning? Save. Okay, so let's go back to this. Okay, so now remember, okay, so I'm sorry, thank you for pointing that out. First of all, thank you, Omar, for pointing out my mistake, and thank you, Rena, for realizing that I made a typo. I appreciate it, okay? So, okay, so now guys, the floor. Well, we know that the floor, the dead load and the live load together, right? Because it's everything specified. In other words, I can just add them together, multiply by my tributary width. And like I said, here, the only thing you have to remember is that I have a beam here. So whatever is on the floor is going to go to that beam and half is going to go to that wall. So therefore my tributary width here is half of 13 feet, 10.5 inches. And that's why, guys, you take your time. Before I do this, believe it or not, I make a sketch of my cross section. You understand? I make a sketch of I do my geometry first. And then on my geometry, I list, for example, my materials. I list my materials here. I list my materials here. Well, this I've already done. I know what this is. So you understand? So from my geometry, I do my list of materials. From my list of materials, I do my loads. From my loads, I then, continue. So guys, there's a very, let's call it systematic way of, one thing allowing you to move to the next one, So I recommend that if you're going to be doing this for yourselves, like get into that practice. So here's 1.0 and 1.9 multiplied by 2.11 meters. Wow, I didn't make that mistake here. Fantastic. So you can appreciate that the wall doesn't really add that much. Okay, the floor does. Of course, that's because of the live load and this because of the snow load, but the wall doesn't really add that much, 1 kilonewton per meter. Of course, the foundation wall is significant. Okay, so we've already calculated that in kilonewtons per meter. So we don't have to worry about that. We have all the same units. And also the assumed strip footing. We assumed it to be that. So now I've got so basically, guys, the way you're supposed to see it, right, is like this, okay? Like the way I see it, that here's my roof. I have a distributed load going across my roof of this much. Here's my wall. I have a distributed load of this much. Here's my floor, a distributed load of this much. So all along my foundation wall here, okay, going down to, or like I should draw it here, so like all along this, oh, I should say all along the strip footing here, okay, I have a distributed load that's acting all along that footing, and that's of course going to be the last amount here of 38.29 kilonewtons per meter. So that's how I calculate the load on my footing, okay? Now, last year when we were doing strip footing, that I say the strip footing has a live load of 1.5 kilonewtons per meter, and now you can actually calculate that, okay? And of course, to size the footing, right? To size the footing, I just need to add them all up together. Now, whatever I assume for the isolated footing, I assume 50 kPa. Well, I'm going to use, of course, have to assume the same soil pressure for the strip footing because I'm assuming it's the same soil condition. And therefore, let me clear this. So if I take my P over my Q allowable, 38.29 kilonewtons per meter divided by 50 kilonewtons per meter, the width of the footing is about 0.766, which is approximately 30 inches. And guys, I strongly recommend, okay, that even if you go down to 24 inches, do not go below 30 inches for the width of a residential footing, okay? Even if your soil pressure allows you to go down to 24, keep it to 30 inches minimum, okay? Go 30 and then use multiples of 6, 30, 36, 42, 48, and so on, okay? So in other words, 2.5 feet, 3 feet, 3.5 feet, 4 feet, and don't go into 2.5 feet or 2 feet, 10, like it's use multiples. And guys, don't worry, okay? Make your footings big enough so that you don't have a problem with settlement, because that's the worst thing that can happen. Once it starts to settle, it's all kinds of money. So when they're building this thing, to pour that extra concrete, it's peanuts. Because keep in mind, for a strip footing, okay, the amount of formwork is the same whether it's, like you did this in estimating. So the amount of formwork for the strip footing is the same whether I have 30 inches or 36 inches or 42 inches. It's always the same amount of formwork. The only thing that differs is the amount of concrete, and that's peanuts at the time that you're building your construction, and therefore that extra 6 inches of concrete is probably your waste factor of 10%. Okay, just to let you know, that's how much it's going to add to the cost of your concrete for your footing. So it's peanuts. So like I said, I've been involved in files where the guy did a very academic calculation. He had a Q allowable of so much. He ended up with a 24-inch footing, yeah. And then all of a sudden he didn't realize that there was some lateral load that was being transferred to his footing, and therefore he didn't have a uniformly distributed load. And if he would have gone to 30 inches, he could have saved himself a lot of hassles. So there's sometimes you overlook things that can affect how the soil pressure, because here we're always assuming that the soil pressure underneath the footing is uniform, right? But keep in mind, we do have some lateral loads that are acting on the wall. These loads can somehow transfer here, especially if it's connected, and these loads can be connected here, and all of a sudden you start getting a non-uniform load, and therefore, by making it wider, it can probably cover for that situation. So keep that in mind, okay? So, and guys, that I think is about it. What do you think? Are the diagrams clear enough for you to follow?
Yeah, they are. Just quick question, sir. For the you're showing us here the sketch. Do we have to attach this kind of a sketch on our?
No. I just want you to put the loads. You understand?
Yeah.
Because look, Omar, this is for you. You're gonna the better you do your design brief, the better of a reference document you're gonna have to fall back on if ever you're gonna be doing this on your own.
Okay.
You follow what I'm saying? Like I'm trying to make you guys build your own little reference book that, hey, I'm gonna be building a house. Okay, let me go through my design brief. You follow? Because your design brief is gonna give you the order on how you're gonna be doing everything. Okay, so guys, stop worry about, guys, when I used to go to school, okay, guess what my objective was?
to build a house. I don't know.
No, my objective was to know as much as I could. So this way, when I would go into the real world, I'd feel that much more comfortable to handle any task that was given me during my career. Does that make sense?
Yes, sir.
Okay. Want to hear one of the saddest comments I hear from our graduates?
What?
Sure.
They come back and they say, I should have taken the program more seriously.
Wow.
Because they realize that there's a lot of things they come across in their career that they've learned about in class, but if they would have paid a little bit more attention, they wouldn't have been, as we say in French, dancing around. You understand? They would have felt more comfortable when they faced it. You see? And that's really unfortunate, because it is, we try to teach as much as we can, and it's up to you to try to take in as much as you can so that you feel comfortable on being able to, I learned hydraulics, you understand? I knew that I wasn't going to become a hydrologist, but man, I can tell you, I really appreciated that course, okay? And just to show you the fact that I appreciated that course, I really paid attention. You know what I did with my hydraulics course?
What?
Okay.
Nothing.
No, on the contrary. I was working for this company, right? And we had to control some flow, right? We had to control some flow. And we had to have ditches. Now, guys, I don't know if you've done any ditch design with Mrs. Barbaruzzi, okay? Open channel flow, have you?
Yes, we have.
Yeah,
Okay.
I think
Yes,
so.
sir.
Okay, so open channel flow, right? So basically, you guys are aware that ditches have to be maintained, right?
Yes.
Every once in a while, they got to go back and they have to pick up whatever is built up at the bottom of the ditch. Agreed? Okay. So what happened is that we had this ditch, right? We had this ditch, and the ditch came along an area that was very convenient for the equipment to improve, to do the maintenance of the ditch, right? So what I did is I calculated here a very rapid flow so that all the fines would not settle here. And then I changed the slope here so that all the fines would fall out here. And then so therefore, this is the only part of the ditch that had to be maintained. It was very convenient because it was right beside the road. And I did all that calculation based on those flow equations. So was I happy to? And then when I went to see the result, everybody was so happy. You see, so I took what I learned in my hydraulics class and I applied it to a real situation, and I was able to do all the calculations and get, and what's really nice about it is that after 2 years, wow, look, they went in there, they dug up the sediment, and then it flowed for another 2 years. Was I proud?
That's pretty
You follow what I'm saying?
impressive. Yeah.
Okay. Now, did anybody teach me this? No. I just took what I learned in my hydraulics class and I applied it to a situation. But because I knew how the velocity affects the sediment to deposit, right? I took that concept and I applied it to the situation. You see? And guys, I can tell you, I was, look at this, okay? I was given this other little project where they had built this crane. It's like a hoist, a hand hoist, okay? It was all built, and they needed an engineer to seal it so that they can use it in the workshop for a company I was working for. And they gave me all the dimensions of everything, the size of the things and this and that. And they wanted to know what would be the lifting capacity of the hoist. So I had to calculate the lifting capacity when the hoist was like this, when it was in one direction. I did all the calculations, okay? And then of course we did a load test to confirm my calculations. And when the hoist was in a certain direction, right? The guy only had 5-pound weights that he could add to the hoist. So, and I had calculated that when it was in this position, the whole thing would tip over at 37 pounds. Okay, I calculated the whole thing would tip over at 37 pounds. So when we were doing the test, the guy put down his 35 pounds and I says, be careful, it's gonna tip now. He went to put the other 5-pound weight, guess what happened? It tipped. So was I proud? Okay, and here, so what's nice about what's nice about the numbers, guys, it should predict what's going to happen in reality. And that's what I love about the numbers, is that it gives you a way of evaluating if this is a situation, given all these variables, and if I can fix these variables, what's going to happen if I, now that I can do these calculations, what's going to be the outcome? And that's what school's all about, being able to predict the outcome. You understand? And guys, enjoy. And I mean, like, for those of you that took the program seriously, I think that's the best thing for you guys to do. For you that don't take the program seriously, well, I can tell you, one day you're going to be sitting somewhere and you're going to say, boy, I should have listened a little bit more attentively when Mrs. Barbarosi was talking about that particular problem, because here they are talking about it, and I would have been able to have a better understanding of what's being said. Because guys, you guys are going to be sitting in meetings, you're going to be sitting somewhere, around other people. And, I'm not saying that you guys are going to become structural engineers, but when a structural engineer starts talking around the table, and if you're following my courses, you're going to be able to relate to what he's saying much more than if you didn't take these courses. Understand? If he starts talking about moments, shears, and, this and that. So, that's what's good about the course. It gives you a good overview of all the different disciplines that we have in civil engineering, and you'll be able to integrate much easier. So it's up to you guys. Look, the old saying is that you can lead a horse to water, but you can't make him drink. So we can only teach you so much. It's up to you guys to learn. It's up to you. Okay. So that's all I can tell you as from my 40 years of working as an engineer. But I can tell you, when I went to school, I was definitely interested in learning as much as I could. And I have no regrets. Like, guys, I used to, I don't want to, if I go back, I used to study 7 days a week, 16 hours a day. That's what I did when I was in school. Okay. And then when Christmas break came, I knew I deserved that break because I put in the time. When spring break came, I really went out and enjoyed myself because I put in the time. And then when my summer came, I really enjoyed my summer because when I was in school, 7 days a week, 16 hours a day, that's what I used to give so that I would be able to grasp as much as I could from all the course that I was taking.
So did you have cell phones back then? Because now with our problems, it's like with the cell phones.
We had those, those cans with the string attached to it. but mind you, the provider was very cheap. There was very little cost. Do we have cell phones? No, but you see, Omar, what you have to appreciate is that if I would go back and have the tools that you guys have at your fingertips, God, you understand?
You would study for 2 days only.
Not that. It's like I would learn how to master the tools.
True.
Do you follow what I'm saying? Okay. I like, guys, I can tell you when we were doing structural analysis, we were doing it
Just
all.
to say something, like you're one of the teachers that manages all the programs the best. Like
that's true.
Like,
that's true.
Like the Zoom, like everything. I was like very surprised of how well you manage everything. I'm like, it's really good.
Oh, you find that I do the Zoom well? Is that what you're saying?
You've handled this situation.
Like even like the Zoom meetings, like everything, like all the props that you can get, like a lot of teachers struggle a lot.
Well, look, last
I was
year.
thinking, like, do you guys get like a training on this? Because
no, I think because they don't wanna like they feel it's a situation that it's not gonna last forever, so they don't want to learn it. So it's just like I'm just like filling up. I don't know, like that's what I feel. They don't want to like.
Look, Omar, there's one thing I've learned. Don't assume with other people why they're not doing it. You understand? All I can tell you, I better put this on pause. Hold on a second. I'm gonna stop. Oh, yeah, because this is all being recorded. I'm glad it's being recorded. You guys can go back and listen to this as a. Hold on a second. Let me put this on. Where's that pause button? Pause record.